Hello again. Welcome back. We're still talking about section 1. We are on to subsection 2, now thinking about functions defined from formulas. Our learning objectives we're targeting today are the ability to identify independent and dependent variables. We have an essential objective of evaluating a function at a numeric and symbolic input, and to find an input of a function given an output, and probably what's involved in that is either solving a linear equation or maybe a quadratic equation, which were both part of our prerequisite objectives. So our example to tackle this, if you watched the previous video where we were looking at a function about animal names and ages and stuff, felt maybe less typical, not quite as mathy, and maybe you'll be more at home with this example. So our definition, such as it is all about function notation. It's saying that when we want to use a formula, we've got some equations set up here, and basically all we're really saying is we have some variable that is the recipient of all of the outputs, in some sense, of our function. So this Q thing is our output, which is another way to say dependent variable. So that's a connection we'll draw to our terminology from before. And independent variable, predictably, is like our input. So when we think about our inputs and outputs of the function, these are just two different ways to think about how that information is stored. I'm sorry, more terminology, but dependent variable is our output, independent variable is where our inputs go. And then the name of the function is f. So as a concrete example, because it tends to feel better when we've got an actual real example to work with, here's one potential relationship for us to think about. So p in this case is a variable, f is the name of our function, n is another variable, and then here's the formula that actually gives us the rule of our function. So what's different here than before, with just an example where everything was given in a word description and a table, is that now we're looking at a function, and the only way that we have to connect these things is by this expression. 8 minus n squared is how we get values for p. So our first question there is about dependent variable, and I think we can work with this pretty reasonably. If we look at this expression and we're asking ourselves about inputs and outputs again, dependent variable is what goes with the output. This is where our function results end up. And in that case, that's the variable basically on a side by itself. It's just waiting for us to process this expression in order to get a number. So our dependent variable in this case looks like p. This is our output. And then almost by process of elimination, if you will, which is the independent variable, and it's the only one that's left, but it's also the one that tends to show up on the inside of these parentheses, because this is where we would pick some value. This is independent in the sense that like we get to choose this number, and then dependent in that once we pick that number, it really doesn't, p doesn't get to pick its value. It's entirely dependent on what kind of falls out of this formula here. But our independent variable looks like n, and that's our input. As far as actual computing stuff, this is the first time we're going to use this notation to really try to accomplish the goal of using a formula with this function. So let's think. Here is our value inside the parentheses there, and if I'm just mirroring things, this has to be n. It's exactly in the spot where this n is supposed to be. So the thing I'm going to try to think to myself is that we're essentially just letting n equal -3. So then when we go to compute, we should be looking at this as some kind of use of this formula, f of n. And if n is really -3, then everywhere we see n, we really ought to be writing -3 instead. So here's n, but there is also n. So f of -3 is equal to, and I'm leaving those blanks there for a second on purpose, something squared. And then I'm basically always trying to think about kind of carving out space. Where n used to be, now we have the number -3, and that's true in both of these places. And then when we go back, now we notice there's actually a numerical value we could get out of this. So 8 minus, and then I got to be real careful. That's why I drew these parentheses here. We want to square this entire input. The input is -3, so -3 squared is actually +9. And last of our little arithmetic there, 8 take away 9, we're looking at -1. So we can reward ourselves with a nice little box of completion there that says, nice job. All right, so that means that if our function were to be given an input of -3, then the output would be -1. So this is a classic kind of function machine diagram where we have our input here on the left, we pass it into this function. I sometimes think of this as like a little conveyor belt that's taking this -3 through some machine. The machine kind of stamps it out. You ever watch that as How It Works programs? Those are pretty neat, where you get to see how, I don't know, mannequins are made or yogurt or whatever. And so this machine does its magic, and then out the other side comes this new output. And in this case, the magic is not very magical at all. It's that we take whatever the input is, we square it, we take 8 minus whatever that result is, and bada bing, bada boom, there's our output. So this is how our formulas are working for functions. We can put things into functions other than numerical values too. We can put in more complicated expressions. It's more annoying, but still totally doable. So now in this case, we're evaluating our function, and a is some constant. So odds are pretty good that our final answer is still going to have some kind of a in it, since we're not really sure what that value is. So I'm going to try to mirror exactly the structure that we had up above. F of something is 8 minus something squared. It's just that now that something is a little more complicated. Now instead of -3, like it was a minute ago, our input is this whole expression, a squared plus 2. So now everywhere there used to be our input variable is instead this annoying expression. It turns out that's usually the hardest part, although algebra does have its struggles, of course, but making sure that parentheses are working out right, that things actually get replaced in the appropriate way, that's kind of the toughest hill to climb usually. There is one little exception here, because there's always an issue, well, potentially an issue, with squaring things like this, because what I really have to do, a squared plus 2 all squared, as soon as we write this out the way it really is meant to be, we're less likely to make a foolish error. But remember, something squared means that thing times itself. And maybe we can try to say the same word at the same time. So in order to accomplish this, we would have to, if you said FOIL, that's probably what your United States high school education probably gave you. I despise the word FOIL, but it has its purpose. So first, outside, inside, last, F-O-I-L, FOIL. So really what's happening though is this is the distributive property. And that's kind of what I prefer to think of it as. But if you say FOIL to me, I'll die a little bit inside, but I'll get over it. It'll be okay. So this says everything in one set of parentheses needs to get multiplied by everything in the next set of parentheses. So FOIL, or the distributive property, which is really what's happening, would give us something like, what is that? A squared times a squared is a to the 4th. We'd have a 2a squared, another 2a squared, and a 2 times 2, which is 4. And the reason I'm kind of doing this on the side is, I mean, we could have done this as part of our work here, but it'll make our function computation a little bit less messy if we put it all in one spot. So the main thing I want to be careful about now is we're getting all this good stuff from over here. Maybe I'll even keep it in black so we can keep track of where all this stuff is coming from. We have a to the 4th. We have 4a squareds, and we have 4 more. And so the main thing I think at that point that could be missed is that we are subtracting everything here. So we're subtracting this entire expanded expression, which means parentheses are a must, because now we're going to be subtracting each of those terms. All right, so when it all comes down, we've got minus a to the fourth. We have minus 4a squared. And then this is the only little excitement where we get to combine some stuff. This looks like 8 minus 4 for a net result of plain old 4. And then we're in business. We reward ourselves with another little box of completion. And we made it happen. And as feared, promised, expected, however you want to think about it, we ended up with an expression that still does have a in it. We didn't have anything that helped us cancel that out. So this is definitely a more complicated application of this function notation, but functions are pretty versatile. They're ready to take in numbers. They're ready to take in expressions that we may not have a whole real number value for just yet, but perfectly good number in the end. Last thing to accomplish looks very similar to what we were just up to, except that you'll notice we're trying to find values of n. N is actually the input. This is our independent variable in this case. So here we know what the output is, and we just don't know what number got us there. But here's where I want to make sure we make use of, I would say, the most valuable tool in mathematics, which is the notion of substitution. If here is where f of n lives, and we go back, here's our formula for f of n. This equal sign is a sacred bond. It says this f of n, everywhere you see that, you would be just as correct writing 8 minus n squared. So if we see f of n, 8 minus n squared is a perfect replacement for that expression. So if we head back down to our exercise here, f of n, that's just as good as 8 minus n squared. So we should be able to perfectly substitute the expression f of n for 8 minus n squared. And then the rest of our equation just is hanging out on the side there. But making that leap, again, sometimes it's just this first step that's the hardest. But making that leap is so important because now we're back to just a plain old algebra problem. We've got ourselves an equation. We have one unknown. It's being squared, which is a little bit annoying, but you know what? We'll manage it. So then we're down to just our regular old algebra skills. We can take away 8 from both sides. So we're down to negative 4. That makes me a little bit nervous because I see this n squared, but remember that we have this negative on this other side, so I'm hoping I'm not going to have to square root a negative because that is generally bad news. So if we multiply both sides by negative 1, thankfully, okay, my heart rate goes down a little bit because now we're back to positives. And then n squared equals 4. The only thing that's a little dicey here is to remember that when we introduce a new square root, because that's how you would get rid of a square, is typically by having a square root. Square roots are all well and good, but there's no guarantee that we knew whether the number underneath that square was positive or negative to begin with, which means we need to have, yes, a square root, which is great because that'll make this square root go away, but it's positive or negative. If we're being really picky, what we have done is take the absolute value of n. When we take the square root of the square of n is really the absolute value of n. That's where the plus or minus comes from, but really when we're solving equations, typically that falls out as plus or minus square root does the job great. So that means there actually are two potential solutions here. Either n is positive 2 or n is negative 2. Those are both great answers. And again, can give ourselves a little box of completion. So that is us using formulas that have defined a function to do some evaluation and some solving. We'll come back with yet another approach to functions here shortly.